In this section we're going to look at the variable oxidation states of transition metals. Starting off with this table, which looks a little bit scary. Don't worry, you don't need to learn all of these, but some of these you'll be aware of already. It's just to illustrate the oxidation states that some of the metals can have, and the common ions that you'll find these oxidation states. So ones that you might recognise from the oxidizing agent, acidified dichromate, where it turns green, so that's green. That green is down to the chromium 3, and the orange was the dichromate ion there. You might also recognise the manganate ion, deep purple colour. In terms of the ions, so ion 2 is a very pale green, whereas ion 3, we've got this rusty orangey brown colour. And copper 2, you'll probably remember, generally blues, sometimes greens. Here we've got scandium 3 and zinc 2. Those are the common ions of those particular elements. So scandium 3 means that the scandium ion is always empty in terms of its D subshell, and zinc 2 plus means that that is full. So there's no transition of electrons possible, and these compounds have no colour, so they're not strictly transition metals. Here we'll pick on one particular element and look at the variable oxidation states within compounds of vanadium, and hopefully we can see that we have oxidation states of +5, +4, +3 and +2. In terms of the colours, the VO2 plus starts off as a yellow colour, and we can sequentially reduce this down. The +4 oxidation state being a blue colour, the 3 plus ion being green, and finally once we've got to the 2 plus we have this violet lilac colour. To put the equations together, we just separately do the two half equations, so the way that I would do this. So we've got the VO2 plus, and then leave a good space, go into the VO2 plus. To start with, we want to balance the oxygens by adding water to the right hand side, and you can see that this means that I'll now need 2 hydrogen ions on the left hand side. I just need to balance the charge now, so I've got 3 plus on the left hand side, 2 plus on the right hand side, so I need 1 electron on the left hand side. For my zinc, so this is for the oxidation of zinc, and zinc will oxidize to form zinc 2 plus, much easier to do, so I just need 2 electrons on the right hand side. So zinc is being oxidized, so this is my reducing agent. To put these two half equations together, I just need to consider the electrons. So I have 1 electron in the first one and 2 electrons in the second equation, which means I need to multiply my vanadium equation through by 2 for my electrons to disappear. So we should get that. Always worth checking at the end to check the charge. So I've got 2 lots of +1 and 4 lots of +1, so I've got +6 on the left hand side, +4 and another 2, +6, so +6 on each side, so I would be fairly confident that this is correct. Do the other two just in exactly the same way. So I'm going this time from VO2 plus to vanadium 3 plus. I need one oxygen on the right hand side to balance that, which means I'll need 2 hydrogen ions on the left hand side to balance the hydrogens. I've got charge of 4 plus on the left, 3 plus on the right, which means I just need 1 electron on the left. My zinc, exactly the same as before, and again I need to multiply my vanadium equation through by 2, and we should get that. Again, check the charge, 8 plus on each side. The final equation's even easier, there's no waters or hydrogen ions involved, so we're simply going from vanadium 3 plus to 2 plus, which means I just need to pop 1 electron in there. My zinc, same as before, so there's 2 electrons, and again, to balance the electrons, the vanadium needs to be multiplied through by 2, which leaves that as my overall equation.